Okay, we're going to be talking about conservation of energy again, prototype 6A. In this case, we're going to be talking about an isolated system. The system is the object, earth, and surface. Recall previously that it was only the object and earth. Now we're going to include the surface in there. It is isolated. We allow no energy to transfer out of the object, earth, surface system or into the object, earth, surface system. Once again, I draw my diagram of mass. It's sliding down the incline at distance d. My x-axis is arranged so that it is parallel to the surface of the incline, y-axis perpendicular to the surface of the incline. What is the external work done on the system? Once again, we can calculate what the external work is, and that comes from the previous example. At this point, as far as the external work, it's 0 because there is no external work. Why? Because we've isolated the system. In the previous example, the surface did work. Now that's part of the system. So there is no work, no external work. It is isolated. What energy leaves or enters the system? And we denote that by change in energy cis, sub cis. And that's equal to 0. How did we write the energy equation for the non-isolated case? If you recall, we had the frictional term on the left-hand side, and we had the two internal energies, the potential and the kinetic energy changes on the right-hand side. So we wrote it as minus the work of friction through distance d equal to the change in kinetic energy plus the change in gravitational potential energy. Let's move the friction term to the right-hand side. Now we have 0 representing external work equal to the change in kinetic energy plus the change in potential gravitational energy plus a new term related to the friction that we call internal energy. It is an internal work done, and that is your change in energy of the system. Now we define the internal term, the friction, and we denote it as change in internal energy. So we can immediately talk about a couple things. One, as the block slides down, is the change in kinetic energy increase or does it decrease? What about the change in potential energy? Does it increase or decrease? What about the term here? Does the internal energy increase or decrease? You can think of this internal energy of friction as generating heat. Will heat be generated or not by friction? Okay, so internal energy increases. Now for an isolated system, we write delta E cis equal to delta change in kinetic energy plus change in gravitational potential energy plus change in internal energy. Let's calculate change in kinetic energy just as we did in the previous example. And we have change in kinetic energy equal to minus the change in gravitational potential energy minus the work of friction over distance d. Of course, the change in gravitational potential energy is a minus mgd sine theta. Now, if you don't know where I got that minus mgd sine theta, I need you to think about it a minute. Now we can calculate VF because we know what the change in kinetic energy and how it's related to the final velocity. We know the number, the actual number of the change in energy or change in kinetic energy is 12.2 joules. So for an isolated system, all we write is that 0 is equal to the change in kinetic energy plus the change in potential energy plus the change in internal energy. And it's important to note that this change in potential energy may include terms from the change in gravitational potential energy as well as terms from change in potential or elastic potential energy. End of discussion.